In this video, we will be looking a little more closely at the definition of a dot product of two vectors. In trigonometry or in physics class, you might have learned that the definition of the dot product is that it's the product of the two x coordinates added to the product of the two y coordinates. And you get a scalar, you get a real number, you don't get a vector as the result of a dot product. That is all true. However, there's a little more to the story. I have two generic vectors, vector A and vector B. We're going to use lowercase a and b for the lengths of vectors A and B, and capital A and B for the angle that the two vectors make with the positive x-axis. These vectors are both in quadrant 1, but it doesn't really matter what quadrant the vector terminal points are. What we're going to state ends up being true no matter where the vectors are located. I've also written the vectors in their component form. So using the right triangle definitions of cosine and sine, the x-coordinate of a vector is always its length times cosine of the angle made with the positive x-axis, and the y-coordinate is always the length multiplied by sine of the angle made with the positive x-axis. So I'm going to follow our dot product definition using these components. So I'm multiplying both x-coordinates together, I'm multiplying both y-coordinates together, and let's do a little bit of algebra on that. I'm going to factor out the a times b, because lowercase a and lowercase b, the lengths of the vectors are in both. And then I'm going to write what we have left. So we have cosine of a plus sine of a, and then cosine of b times sine of b Okay, so this is equivalent to what we have up here, which is equivalent to the dot product. Now, if you studied your trig identities, and I know at the time you're sometimes learning trig identities, they may seem like rules that don't apply to anything, but here's a good use of the difference rule for cosine. Notice we have cosine of A times cosine of B plus sine of A times sine of B. That is equivalent to cosine of A minus B. I'm just following the difference rule for cosine. So A minus B, and remember for cosine, cosine of an angle is equal to cosine of its opposite. So for the way we have our picture drawn, what we're going to state might make a little more sense if it said B minus A. But for cosine, the angle, an angle doesn't matter if it's negative or positive, you're going to get the same value for cosine. So these two values would be equivalent to each other. So notice we have the product of the lengths times cosine of the angle in between the two vectors. If I take vector B and I subtract vector A, I'm going to be left with this angle here. This is angle B minus A. Again, the way I had it originally written, we have A minus B, which will just be the opposite number of B minus A, but cosine of it will be the same. So that is another important way to look at the dot product. The dot product is equal to the product of the length of the vectors times cosine of the angle in between, and that is also equal to the product of the x coordinates added to the product of the y coordinates. Some other important aspects of our definition of dot product is that this relationship of the product of the lengths of the vectors times cosine of the angle in between being equivalent to the sum of the product of the components is that it can be rewritten in terms of cosine of the angle in between. And you will see this as the definition on how to find the angle in between two vectors. It'll say cosine of the angle in between two vectors is equal to the dot product of the vectors divided by the length of the vectors. And by the way, that's equivalent to the dot product of the unit vectors. Because remember, a unit vector is basically a vector divided by its length. And so if you dotted the two unit vectors, it would be equivalent to the calculation we have here. And by the way, if your angle in between your two vectors happens to be 90 degrees, cosine of 90 degrees is 0. So this product of taking the lengths and multiplying it by cosine of the angle in between will yield 0. So that's a way to tell whether or not two vectors are perpendicular. If their dot product is 0, you know the vectors are perpendicular. And then we also have a definition from physics about work, and the definition of work is force times distance, but in terms of vector calculation, it's often written as the magnitude of the force times the length that the force was applied times cosine of the angle in between the force direction and the movement direction. And that comes from the definition that we were just working with up here. And so again, you'll see this definition of work in physics books, and it's really just an application of dot product.